see from the title of this video, this tutorial is about learning how to balance equations. There is a law. It is called the law of conservation of matter that says in an ordinary chemical reaction, meaning non-nuclear, that matter cannot be created or destroyed. What that means is when I have a chemical reaction, like the ones listed here, I have to have the same number of hydrogens on the left side as I do on the right side. Otherwise, I created a hydrogen atom or I destroyed one, which we know isn't true because we know mass can be conserved, therefore matter can be conserved. So whenever we work with chemical equations, we have to balance them to make sure we are in accordance with the law of conservation of matter. If we're going to balance equations, we try to break it down into a series of steps if I'm looking at the equation. I've listed those steps here, and we'll go through them. Step 1, identify the reactants and the products and write equations for each. Sometimes this will be done for you already. For instance, in this example here, I already have the equations of each of the compounds or elements listed. Other times we'll start with them in words and you'll have to write the formulas first, then go back and balance. But we'll do these first and then we'll add them. Step 2 says break the equation in half at the arrow and list polyions that appear on both sides of the equation as single units. Then list the other elements. For instance, if I have the polyion SO4 on the left side and SO4 on the right side, I do not need to break that apart into its individual elements. I am able to keep it together as one single unit, and you will find it saves you a large amount of time when you go to balance. Step 3, balance polyions that are not hydrogen and oxygen. We always save hydrogen and oxygen for last. So we balance our polyions, we balance the other elements except for H and O. It says here, watch for the half method or the LCF, where LCF stands for least common factor. Sometimes to get the elements and the polyions to balance, we will have to do something called the half method or find the least common factor between the two. Last but not least, it says balance H and then O last. We save hydrogen for second to last and oxygen for very last. And just like you have to watch for the LCF or half method here, you do here as well. So the best way to get practice at balancing equations is by simply doing it. So up here I have listed 6 different equations that we're going to balance. First thing we'll do is we look at the equation. Take a second to copy that down. And now we're going to try to follow our steps that will lead us to getting this equation balanced. First thing we do, identify the reactants and products, write equations for each. That is already done. Step 2, break the equation in half at the arrow and list polyions that appear on both sides of the equation. Well, I don't see any polyions here, so we don't have to list them. Then, list other elements. So I list the other elements that I see. I see hydrogen, and I see oxygen. I see hydrogen, I see oxygen. The next thing you do is you list how many of each that there are. Because there's a subscript of 2 here, and no coefficient, which means it's a 1, that tells us there's 2 hydrogens on the left side. Same thing here. A coefficient of 1 and a subscript of 2 tells us we have 2 oxygen atoms. Looking over to this side, coefficient of 1 and a subscript of 2 tells me I have 2 hydrogen atoms, and a coefficient of 1 and a subscript of 1 on the O tells me I have 1 oxygen. So the first thing I do is I check to see if it is balanced already. 2 H's, 2 H's, H's are balanced, 2 O's, 1 O, O is not balanced. So if I were to leave it this way, what I am representing here is that I destroyed an oxygen atom, which cannot happen according to our law of conservation of matter. So what we will do is we will try to balance this equation by using coefficients. The only place you can put numbers into the equation is in front of compounds. Here is why. H2O is water. I would fill up a cup of it and drink it readily. Somebody may say, well, why can't I just put a 2 here? Now we're balanced. 2 O's, 2 H's. H2O2 is not water. H2O2 is hydrogen peroxide, which we use to clean cuts out. I would most definitely not drink hydrogen peroxide. So we can never touch the subscripts of an equation. All we can do is put coefficients in front. So according to this, we're going to balance polyions that are not H and O, and then, balance polyions that are not H and O, and the elements that are not H and O. So all I have is H's and O's, so I have to move to step 4. Balance H and then O last. Well, H was good. I have 2 O's on the left, I have 1 O on the right. I can't put a 2 after the O, so the only way I can get there to be 2 O's on this side is by putting a 2 here. 2 times the 1 O gives me 2 oxygens. However, putting a 2 here doesn't only affect the O, it also affects the H. Now, instead of just having 2 H's, I have 2 times 2 H's, I have 4. That's no big deal. Then, if we unbalance something, we just go back and refollow our steps. My step next says balance H, because I just have H and F. Well, now I have 4 H's on the right and 2 on the left. So I have to think of a way I can get this to give me 4 H's, and hopefully you came up with a 2 in front here. 2 times 2 gets me to 4 H's, and now the equation is balanced. 4 H's, 4 H's, 2 O's, 2 O's, and you'll see that a 2, 1, 2 ratio gets the equation to be balanced. Anytime a question asks you what the molar ratio of something is, they're simply asking you what are the coefficients in front of each of these compounds. Let's take a look at letter B. Letter B says Na2O plus H2O yields NaOH. Try to follow our steps. Identify reactants and products and write equations for each. We have already done that. Step 2. And let's change this just so we don't get confused. Write formulas for each. Step 2. Break the equation in half at the arrow and list polyions that appear on both sides of the equation as single units. Well, I see OH on the right, but I do not see OH on the left. That means I can't keep it together. So we have to break it down into all the elements that we see. So I see an Na, I see an H, I see an O. Over here, Na, H, and O, same thing. If ever you don't have the same things on the left as you do on the right, that means you made a mistake, because there's no possible way you could balance it if you don't have the same things. Now we'll list how many of each we have. Coefficient of 1, subscript of 2 means I have 2 NAs. Coefficient of 1, subscript of 2 means I have 2 H's. First time we do something a little different, I have oxygen in both compounds, so what do? Well, I have a coefficient of 1, subscript of 1, means there's 1 oxygen here. 1 and 1 means 1 here, and then I do what the sign tells me. I add them. So I have 2 oxygens, 1 from here and 1 from here. Over here, same thing. All subscripts of 1, coefficient of 1 means I have 1 Na, 1 H, and 1 O. So my equation is not balanced. So I move on. The next thing it says is balance the polyions and the elements that are not H and O. So according to what I have listed, I have to balance sodium first. So I have 2 on the left side. I need there to be 2 on the right side. The only time I can put numbers in is in front. So if I put a 2 here, I get 2 times Na. Now I have 2 NAs. However, that's not the only thing I affected. The 2 will also reach O, making it a 2, and H, making it a 2. And sure enough, by doing that, it balanced the other two elements for me. That is why we save O and H for last. Reason one is that they appear in a ton of different compounds. In reason two, because they appear in a lot of compounds, they get split up a lot, and it makes it easier to balance if you save them for the end, because a lot of times it will take care of itself. Let's take a look at another two. Letter C says, Fe plus H2O yields Fe3O4 plus H2. So we'll follow our steps. First step says, write formulas for each, we are good. Step 2 says, break it in half, down the middle, list the polyions that are on both sides. I don't see any polyions, so we go and we list the elements. Over here, I see an Fe, I see H's, I see O's. Fe's, H's, O's. Then we count how many of each that there are. Over here, I have one Fe, two H's, one O, three Fe's, two H's, four O's. So the equation is obviously not balanced. So according to our rules, I balance H and O last, so I have to start with Fe. I have three Fe's on the right. How can I get there to be three Fe's on the left? I put a coefficient of 3 right there. Now I move on to H and O. H, I have 2 on the left and 2 on the right, so we are good. And lastly, O, 1 on the left, 4 on the right, I'm not good. So if I have 4 O's on the right, how can I get there to be 4 O's on the left? Well, here's the only compound that has O, so I put a 4 in front. 4 times the 1 gets me 4, but I also affect the hydrogen now. I have 4 times 2 hydrogens, that gives me 8. It's okay if you unbalance something. All you have to do is go back and fix it. So Fe is still good. I have 8 H's on the left. I need there to be 8 H's on the right. So I need a number here that's going to take times 2 will get me to 8, and that number is 4. Now I have 8 H's on the right side. At the end, you could probably get in the habit of checking to make sure they're balanced. 3 Fe's here, 3 Fe's here, 8 H's 4 times 2, 8 H's 4 times 2, 4 O's 4 times 1, 4 O's 1 times 4. And that means you are balanced. Let's try the same thing with letter D. C2H4 plus H2 yields C2H6. First thing we do, list our formulas. We are good. Then we break the equation in half at the arrow, and we list polyions that are on both sides. Again, no polyions. Now we list our elements. It looks like on this side I have carbon and hydrogen, and this side, carbon and hydrogen. Now we list how many of each there are. Looks like I have 2 carbons here, 4 hydrogens plus 2 more means 6 hydrogens, right? 4 from this compound, 2 from this one. Over here, just 1 compound, I have 2 hydrogens, 2 carbons, and 6 hydrogens. So we take a look, and sure enough, this one is already balanced, so I don't have to do anything to it. Simply having the formulas there is enough to have that equation balanced. Let's try 2 last ones. Letter E says Fe parentheses NO3 parentheses 3 plus AgClO3 yields AgNO3 plus Fe parentheses ClO3 parentheses 3. So we try to follow our steps to balance this thing. Step 1, write yourself formulas for each. We have already done that. Step 2, break the equation in half at the arrow and list polyions that appear on both sides. Here is the first example where, yes, we have polyions. And the polyions sometimes are really easy to spot because they come prepackaged in parentheses. So I can see I've got NO3 and ClO3, one on each side. If they have a matching partner on the other side, we can keep those together. So here is NO3, here is NO3, we can keep that together as one thing. ClO3 is a polyion over here. It also appears here, which means I can keep that together. I'm all out of polyions, so now I list the elements that are left. I see Fe and Ag. And on the other side, Fe and Ag. If there were O appearing separately, you would list it separately, just as another element if it weren't built into a polyion. So now we need to count how many of each we have. So if I look on the left side here, NO3s, I have a coefficient of 1 and a subscript of 3 outside my NO3, which means I have 3 NO3s. ClO3, I have a subscript of 1, a coefficient of 1, and here, be careful, ClO3 is the polyion. Right? Because there's no parentheses with a number outside, that tells me there's just one of them. So 1 times 1 just gives me 1 ClO3. Over here, Fe, 1 times 1 is 1 Fe. Ag, 1 times 1 is 1 Ag. Same thing on the right. NO3 is my polyion, so that's kept together. No parentheses with no subscript means there's just one. So I have one of those, 3 ClO3s, 1 Fe, and 1 Ag. So we look, is it balanced? It is not. Right? We have 3 NO3s on the left and 1 on the right. According to this, we'll balance the polyions first. Right? So it doesn't matter if you do the ClO3 first or the NO3. Right? So choose whichever you feel the most comfortable with. Right? But 3 NO3s on the left, how can I get there to be 3 on the right? I have to put a coefficient of 3 in front here. That would take 3 times the 1 NO3, takes that to 3, but it will also take Ag to 3. Okay. Same thing with ClO3, 3 on the right, 1 on the left. Right? That means I have to put a 3 here to get that balanced, taking this to a 3, 3 times the 1, but taking Ag to a 3, but that ended up working out for us because now 3, 3, 1, 3, 3, 3, 1, 3, we are balanced by doing that. So the polyions can be kept together if they appear on both sides, and it tends to simplify things a great deal. I have found that if you can keep them together and don't, it tends to get extremely difficult. Last but not least, Fe plus O2 yields Fe2O3. Step 1 says list formulas for each of those. We have done that. Step 2 says break it in half, down the middle, list polyions that appear on both sides. There are none. So now I list my elements. Fe and O, Fe and O. And now we count how many of each there are. 1 times 1 is 1 Fe, 1 times 2, 2 Os. 1 times 2 Fe's is 2 Fe's, 1 times 3 O's, 3 O's. So it looks like Fe is the first thing we have to balance because we save O and H for last. 2 Fe's on the right. How can I get there to be 2 on the left? I put a coefficient of 2 here. And now to the O's. 3 O's on the right, 2 on the left. And here is the first time we run into a problem where if I have 3 on the right and I want to get 3 O's, there's no whole number here that will do it. Right? If I put a 1 here, it's a 2. If I put a 2 here, it's a 4 and I overshoot it. So there's 2 ways you can tackle this. And that's what this is all about. Watch for the half method or the LCM. Right? With the idea of balancing these odd numbered ones. Right? You can either, if it is the last element, do the half method. And what I mean is you can make this a 0.5 if you need to. Because if 1 makes it a 2 here and 2 makes it a 4, 1.5 will make it a 3. If you do that, we don't leave 0.5s in the balanced equation. You get rid of them by multiplying everything through by 2. Because if I double everything, this will become a whole number. 2 would turn into 4. 1.5 would turn into 3. 1 would turn into 2. And sure enough, if you look, 4 times Fe would be 4 Fe's, 3 times 2 O's was 6 O's. 2 times 2 Fe's is 4, 2 times 3 O's is 6. So we would be balanced. You can only do the half method if it's the very last thing to be balanced. Right? If it's not the last thing to be balanced, you cannot do the half method. So that's how you do the half method. How does the LCF work? Well, I'll start you back from scratch to show you how it works. And it starts out the same way. We list how many of each, which was 1 and 2, 2 and 3. You balance the Fe's, 2 here, 2 here, get us to where we were. What you can then do is if I have 3 O's here and 2 here, and they're contained in one compound, I get myself to the least common factor between them. And the least common factor between 2 and 3 is 6. So what I'll try to do is put coefficients in here that get O to 6. Well, the coefficient here that would make this a 6 is a 3. 3 times 2 is 6. And to get this, 1 times 3 would be 3, to a 6, I put a 2 here, it would be a 6. The catch is, I'll also change Fe to a 4. Right? Well, I have 4 Fe's on the right, 2 on the left. How do I get this side to give me 4 Fe's? Well, I erase the 2 that's there, and I put a 4, and now we're balanced. And notice, you end up at the same molar ratio no matter which way you do it. But I want you to remember, you can only do the half method if it is the very last element to be balanced. The rest of the time, you have to do the LCF. This is pretty much beginner balancing equations. We will do a lot of practice in class, and I'll show you some other things. But if you were having trouble, hopefully this clarified some things for you. You have your steps here to refresh your memory if you were struggling there. Other than that, if you're still having trouble, please come in for some help.